2021 Level 3 Physics Waves examination that I am going through. So, question 1 is about superposition of sound waves. The word superposition means two waves occupying the same place at the same time. Okay, so two loudspeakers are connected to the same signal generator, which is said to make the loudspeakers vibrate at a frequency of 895 Hz, and the corresponding wavelength is 0.381 meters in air. The teacher makes sure that she wires the speakers so that they move in phase. A student uses a phone to measure the sound intensity, which is the loudness, at point A, which is equally distant from both speakers. She moves the phone towards B, noting that the sound gets quieter and then louder again. The diagram below shows the setup. Determine the distance a student will have to move the phone to find the first quiet point between A and B. So what we have to be careful is the formula is slightly different for the quiet point. So what do we know? Frequency is 895 Hz, the wavelength is 0.381 meters, and they talk about the first quiet point, so n is equal to 1. For a quiet point, the formula is n minus half lambda, which is the path difference, is dx over L. So when you substitute, you get the value for x, which is 3.18 meters, and that's an achieved. So here's my unrounded answer, and then it's rounded to 3 significant figures. Now explain how superposition causes the sound intensity to change when the phone is moved from A to B. Now, superposition has to do with two waves occupying the same place at the same time. At A, the waves from both speakers arrive in phase with zero path difference and interfere constructively, creating a loud sound. So you need to use all these three words. Okay, they're really important. Now, as the phone is moved from A to B, the path difference increases. And when the path difference is half a wavelength, which is half of that, the waves reach that point at opposite phase where a crest interferes with the trough, causing destructive interference, and so there's a quiet spot. Moving further away causes further increase in path difference until the path difference is one wavelength, causing constructive interference, and then you have another loud point, and so on. So the point is, as you move from the center outwards, the path difference keeps increasing. So the path difference is 0 here, and then it's half a wavelength, and then a whole wavelength, and then it keeps going. Okay, next one. Describe the difference in the pattern of loud and soft sounds the students would hear as they walk along AB if the speakers were further apart, and give reasons for your answer. So I used a formula for this one. So when the speakers are further apart, the loud and soft sounds would be closer together. So if you just said this, you'd get your achieved. Now the reason is, using the formula, n lambda is d sine theta. As d increases, sine theta will decrease, so theta will decrease, causing the loud and soft sounds to be closer together, and that's a merit. Now the teacher also wants to demonstrate beats, with speaker 1 making a sound frequency of 895 Hz. What she does with speaker 2 is it does a frequency of 890 Hz, and they sounded at the same time. So explain why the students hear a note that regularly changes in loudness and determine the frequency of this beat. Now, since both speakers are producing sounds of slightly different frequencies at the same time, I left out the word time here. Okay, at the same time, these sounds interfere with each other, both constructively as well as destructively. They move through each other regularly, in phase and out of phase, producing loud or constructive interference and soft sounds, which is destructive interference. The beat frequency is a difference between the two, which is 5 Hz. And if you said both those and calculated the beat frequency, you get your merit. Now the question continues, what's going to happen or what's going to happen to the frequency of the beats as the teacher increases the frequency from 890 to 900 hertz. For speaker 2, speaker 1 remains the same. So when the frequency of speaker 2 is initially at 890 hertz, the beat frequency is 5 hertz. As the frequency of speaker 2 approaches 895 hertz, the beat frequency will reduce or decrease until there are no beats when the frequencies are identical at 895 hertz. Now, when she continues to increase the frequency of speaker 2 further, beats will be heard again, and when speaker 2 has a frequency of 900 hertz, you will hear beats again at 5 hertz. Okay, and that's the answer. It goes all the way to excellence if you said all these three things. So this whole thing is one question. Okay, question 2 is on standing waves. The speed of sound in air is taken as 341 meters per second. Mark uses a sort of didgeridoo using a piece of plastic drain pipe. So there's my plastic drain pipe. And Mark vibrates his lips against the pipe, making the air vibrate in the tube and also blocking the tube at the end he's blowing into so that one end is closed while the other is open. So I've kind of just drawn a closed pipe. And what I've just done, which is not asked for, is the fundamental is like quarter wavelength. Okay, calculate the wavelength of the lowest note that Mark can make. So the lowest note is quarter wavelength, so it's 4 times the length of the pipe, and that's you achieved. Now, some of the richness in the tone of this instrument is caused by the presence of overtones, and draw the first and second overtone. So remember, even numbered harmonics are not produced in a closed pipe. And you don't even have to draw the wave, you just have to label the positions of the nodes and antinodes. But I kind of just drew the wave as well, so that you get an idea of what sort of wave is produced. So you always have to have nodes at the closed ends, antinodes at the open end. Your first overtone is the third harmonic, and the second overtone is the fifth harmonic. And make sure your nodes and antinodes are evenly spaced over here. So those distances have to be equal. Now, what are the frequencies? So your first overtone is 3 times fundamental, and the second overtone is 5 times fundamental. They kind of relate to the harmonic number. Okay, although Mark's lips vibrate at many frequencies, the pipe resonates only at certain frequencies, and explain how the sound waves travel in the pipe to produce only these natural resonant frequencies. So there are certain points that you have to make here. So the important thing is, in this situation, only those waves that fit the length of the pipe and the restrictions of the pipe will resonate to produce standing waves. So there's you achieved. Now these standing waves are created when the incident and reflected waves travel through each other. Since the pipe is closed at one end and open at the other end, nodes will have to be formed at the closed end where the reflected waves undergo a 180 degrees in phase reversal. So that's why it's a point of no disturbance. At the open end, there is no phase reversal, hence the fundamental is quarter wavelength, and the overtones will be odd multiples of quarter wavelengths, which are 3/4 and 5/4 wavelengths. So that goes all the way to excellence. As Mark keeps blowing into the pipe, the air warms up. So the speed of the sound in the pipe increases. How will this affect the resonant frequencies of the sound that the pipe produces? So I've used the wave equation here, and so when the speed increases, your wavelength stays the same, your frequency will increase. So if you've just said the frequency will increase, you get A. If you related it to the formula and said that the length of the pipe is the same, and so the wavelength stays the same, you move on to a merit. Okay, question 3, Doppler effect at the racetrack. Susan is watching a Formula One car race. As the cars go past, she hears the familiar sound of the engine change due to the Doppler effect. The speed of the sound in air on the track is 341 meters per second. Now the speed of the car that's approaching Susan is 44.4 meters per second. What she hears, that's the apparent frequency, is 650 hertz. Now, show that the frequency heard by the driver is 565 hertz. So remember, for show that questions, write the formula, substitute, and give an unrounded answer, and there's your answer. Okay? Then explain why the motion of the car causes Susan to hear a different frequency to that which the driver hears. So you comment on what Susan hears and comment on what the driver hears, and you may draw a diagram. So what I've drawn is there would have been a car's picture which is taken off here. So I've drawn the wavefronts close together, so the wavelength is shorter and larger there, and there's Susan standing. So the driver hears the actual frequency as there's no relative motion between the sound waves and the car. So there's your achieved. Since the car is approaching Susan, the sound waves bunch up in front of the moving car, causing the apparent wavelength to decrease. The speed of the sound waves remain the same. That doesn't change. So when wavelength decreases, frequency will increase. So she will hear a note of a higher pitch. So higher frequency means higher pitch. And if you said all that, that's excellence. Now, after the car has passed Susan, it's moving directly away from her, and she hears the engine at a frequency of 500 hertz. And Susan wants to know whether the car is still traveling at 44.4 meters per second. By assuming that the true frequency of the engine has not changed, determine whether the car has changed speed. So if the car was still traveling at 44.4 meters per second, then Susan would hear the apparent frequency using the formula, use substitute, and I get 499.9, which is about 500 hertz. So that means the car is still traveling at 44.4 meters per second. So if you just got this much, that's an achieved. If you commented on and related it back to the speed of the car, you get your merit. Now, Susan knows that as the car accelerates, the frequency of the sound produced by the engine increases. After the car has passed Susan, it accelerates away with an increased frequency of 10% compared to the original frequency. When the car speed is increased by 10%, will the frequency Susan hears be higher due to the higher revs or lower due to Doppler effect? And justify your answers. So this is the new speed. How did I get the new speed? What I did was I just did 44.4 plus 10% of 44.4, and then I got 48.84. The new engine frequency, so that's the original one, plus 10% of that, you get 621 hertz. Then I calculated the frequency Susan's going to hear. So this is the new frequency. The speed of sound is the same plus the new speed of the car, and I got 543 hertz. Initially, it was 499 or 500. So it's gone from 500 to 543. So that's an increased in pitch. So the 10% increase in engine frequency is much greater than the 10% increase in car. So the frequency that Susan hears will be higher. So if you just got so much, it's an achieved, and if you said all this bit, you get your merit. And that's the end of the paper.